Hello, this is Chapter 17, Optimization Linear Programming. Our learning objectives for today are the following. Formulate and solve a maximization linear programming problem. Formulate and solve a minimization linear programming problem. Describe special cases and potential issues in linear programming. Abigail Kwan is an operations manager at Fashion Tech, a manufacturer of clothing for families with an active and outdoor lifestyle. One of the difficult decisions that Abigail has to make every winter season is to decide how many parkers and winter jackets for women to produce. Both products use the same materials and require very similar sewing and stitching skills and manufacturing steps, and therefore compete for the same resources. She starts by focusing on analyzing data for the medium-sized jackets and parkers. The amount of machine time needed to produce a jacket and a parker are 1.5 hours and 2 hours, respectively. A tailor usually spends about 2 hours on sewing and stitching for a winter jacket and about 3 hours for a parker. Fashion Tech has a monthly contract with its supplier to procure 4,000 feet of the required fabric. The amount of machine time allocated to producing the two products is 650 hours per month, and each month a number of skilled tailors are assigned to these products for approximately 900 hours. Historically, Fashion Tech has never sold more than 400 jackets and 150 parkers in a month. The monthly production rate of parkers and winter jackets need not be more than these historical limits. Abigail would like to, number one, determine how many winter jackets her company should make each winter, and number two, understand the impact that each production resource has on the overall profit. Optimization with linear programming. Optimization is a family of quantitative techniques for obtaining optimal solutions to complex problems under constraints. Start with a well-defined objective function. Find a set of inputs that maximizes or minimizes the value of an objective function. Linear programming, or LP, is a simple way to perform optimization by assuming linear relationships among relevant variables. Maximize or minimize a linear function subject to resource constraints. Few assumptions help solve a very complex problem. It's also widely used. The first step in performing LP is to formulate a problem into a series of mathematical expressions. The mathematical representation of most LP problems has four essential components: an objective function, decision variables, constraints, and parameters. Objective function, a mathematical representation of an objective, usually expressed as a maximization or minimization function of a single variable, such as profit or cost. Assumed to be linear. Maximization is profit, revenue, return. Minimization is cost, time, distance. Decision variables, choices or alternatives available to a decision maker maximize or minimize the value of the objective function. The constraints are the limitations due to the limited resources available to the decision maker. It's also assumed to be linear and reflects the knowledge gained from historical data or human expertise, intuitive assumptions about the LP problem. Parameters, numerical values in the LP mathematical expression associated with the objective function, the decision variables, and the constraints. It might be derived from historical data, and input parameters usually remain constant and do not change when the solution to the LP problem is implemented, unless there are changes to the external factors. Example, recall the introductory case. Abigail Kwan wants to use the information from relevant stakeholders in her company to formulate an LP model. Our objective is to determine the number of winter jackets and parkers Fashion Tech should produce in order to maximize the profit from these two products. Let X sub 1 and X sub 2 represent the number of jackets and parkers produced. We want to maximize profit. Profit equals 9X sub 1 plus 12.5 times X sub 2. There are 5 constraints. Fabric is less than or equal to 4,000. Machine time is less than or equal to 650. Labor is equal to or less than 900. Demand for jackets is less than or equal to 400. And demand for Parkers is less than or equal to 150. We also require non-negativity greater than or equal to 0. The mathematical expressions used are called the standard form. This is the most common and intuitive way to formulate an LP problem. In the standard form, the right-hand side of the constraints is usually a constant, and the left-hand side usually includes decision variables. Most software applications, including Excel, Solver, and R, use the standard form to represent an LP model. To gain an understanding of a linear programming technique, we solve an LP problem with two decision variables through graphical representation. The objective function and constraints are linear. Plot the mathematical expressions in a line chart and identify possible solutions that satisfy the constraints. To find an optimal solution to a maximization problem, identify the values of the decision variables that maximize the profit while satisfying all the constraints. Here's the machine time, demand for jackets, and demand for Parkers, and this is all plotted. Here we go. Now add the other constraints, the fabric, machine time, and labor, and the objective. This gives the feasibility region where the optimal solution exists. Optimization with linear program continued. Increase the profit as long as part of the profit line remains within the feasibility region to maximize the profit. Normally, an optimal solution can be found at the boundary or at a corner of the feasibility region. With only two decision variables, we can plot the LP model onto a two-dimensional line chart and find an optimal solution. However, this approach is not suitable for LP problems with more than two decision variables. Use an algebraic procedure called the simplex method or simplex algorithm to manually solve the LP problem with multiple decision variables. The simplex method says that if the optimal solution exists, it will occur at one of the corners or boundaries of the feasibility region. The feasibility region contains solutions that satisfy all the constraints in the LP problem. Don't evaluate every possible feasible solution. By evaluating corners or boundaries, it is more efficient to find the optimal solution even for a complex LP problem. Evaluate a feasible solution at one of the corners of the feasibility region. Then, iteratively move to an adjacent corner to determine if the current solution can be improved. This process is continued until the optimal solution is found. The simplex method can solve both maximization and minimization problems. Example, recall the introductory case. Maximize the objective function given the 5 constraints. With Excel, open the Parkers worksheet, make sure Solver is activated by going to File, Options, Add-ins, and Go. Verify that Solver is under the Data tab, and then navigate to the Parameters section of the Parkers worksheet. This is the example continued with Excel. And the example continue with Excel and launch Solver by navigating to the Data tab and click Solver. Continued with Excel. Optimal values, 300 jackets and 100 Parkers. Use 3,800 feet of fabric of the 4,000 available. Remaining 200 feet is called slack and excess of supply. Uses all the allotted machine time and labor, and there is no slack. Slack is the amount of available resources that are not exhausted when an LP solution is implemented for a maximization problem. Surplus refers to the amount in excess of minimum requirements and the constraints when an LP solution is implemented for a minimization problem. Binding constraints without slack or surplus, increasing or decreasing the resources will impact the LP solution and optimized values. Non-binding constraints have slack or surplus. Adding or reducing the non-binding constraint value by 1 unit will not change the LP solution. Recall the introductory case and consider the sensitivity report. As we go here and we take a look at the chart here for final value, reduced cost, coefficient, allowable increase, allowable decrease. Shadow price, dual price, the change in the optimized value of an objective function due to a 1 unit change in a binding constraint, holding all other parameters constant. Note that the optimized value of an objective function will not change due to a 1 unit change in a non-binding constraint. In the range of optimality, the range of objective function coefficients between the allowable increase and decrease, within which the optimal solution for an LP problem remains unchanged. In the range of feasibility, the range of values of a binding constraint, and within which the shadow price remains the same. And this is with R. Minimization problems in linear programming. A minimization problem can be formulated and solved in a similar fashion as a maximization problem. We find the values of the decision variables that minimize the value of the objective function. The constraints in the minimization problem usually describe minimum requirements that must be met. As such, a minimization LP model usually has at least one constraint with the greater than or equal to sign. Example: Yerba Buena Tea is a manufacturer and wholesaler of high-quality tea products. Spiced chai is becoming increasingly popular among younger consumers, and Yerba Buena offers 2 chai products, spiced chai powder mix and spiced chai concentrate. An older production facility costs $190 per hour to operate, and for each hour of operation can produce 295 ounces of the powder mix and 260 ounces of the tea concentrate. Because of its age, the old factory cannot operate longer than 8 consecutive hours at a time. Example: a newer facility costs $260 per hour to operate and produces 385 ounces of the powder mix and 375 ounces of the tea concentrate per hour. Yerba Buena also owns a small single-purpose facility that costs $150 per hour to operate and produces 350 ounces of the powder mix per hour. Several coffee shops have placed orders for a total of 5,500 ounces of the chai powder mix and 4,000 ounces of the tea mix. Anika Patel, the general manager at Yerba Buena, has none of the 2 products left in inventory and needs to decide how many hours to operate each facility to fulfill the orders while minimizing the production costs. Formulate and solve this problem for Yerba Buena. In the example continued, X sub 1, 2, and 3 represent the number of hours to operate the 3 facilities. And we're looking at minimize, the production cost here would be 190 times X sub 1 plus 260 sub 2 plus 150 sub X3. The constraints: orders for power mix, orders for tea, old facility operating hours, and non-negativity. Here is the example with Excel plugged in with the different parameters. Same thing here as well, and then with R. Okay. Special cases in linear programming. Real-world optimization problems are usually complex and involve multiple decision variables and constraints. Simplifying assumptions such as linear relationships among variables in the LP model, we can solve these problems. When we formulate an LP model to reflect the complexity of a real-life situation, the LP model may yield more than one optimal solution. In other scenarios, an LP model may not yield any feasible solution at all. These situations may stem from a variety of reasons: missing constraints in the model, or errors in specifying the constraints or parameter values. An LP model may yield multiple optimal solutions that have the same maximized or minimized value of the objective function. This may reflect the diverse options available to a decision maker. This is not necessarily an adverse outcome. It may allow a decision maker to incorporate other qualitative criteria to choose the most desirable course of action. If the allowable increase or decrease of a decision variable is 0, this indicates that the LP problem may have multiple optimal solutions. R and Excel can only show one solution. A linear programming program is infeasible when there is no solution for which all constraints in the LP model are satisfied. Incorrectly formulating some of the constraints and erroneous signs in a constraint. Excel and R will analyze and identify an LP model with no feasible solutions. The source of infeasibility is not always easy to detect, especially in an LP model with a large number of constraints. In many cases, each mathematical expression in the LP model needs to be carefully examined in order to identify the cause of infeasibility. And here we have a chart. Linear programming problems are unbounded when the objective function can attain an infinite value without violating any constraints. Maximization, the objective function, can increase to positive infinity. In minimization, the objective function can decrease to negative infinity. These solutions are not realistic, as it is not possible for companies to continue to increase their revenue or profit indefinitely or reduce cost indefinitely. The unbounded problem is usually caused by mistakes in the formulation of the LP problem. A maximization problem is seriously solved with the minimization objective function. Necessary constraints are missing from the LP formulation. We should revisit the underlying problem and identify any necessary constraints that are not being explicitly included in the model. Well, I thank you for listening.